take a look. So we already know how to solve some logarithmic equations. We already have an idea. In fact, we already have solved some logarithmic equations. Oh, thanks. Okay. We already know how to solve some equations with logarithms in them. Okay, and I'll give you an example here. Okay. For example, I'll do a very simple equation here. So we already know how to do, let's say, like log base 2 of 8 equals x. Okay. Very simple equation, right? It's already technically solved for x here. Technically, it's already solved for x here. But what we could do to kind of continue working, because again, we don't know how to evaluate log base 2 of 8, but we could, remember, rewrite this. Okay, so one option is we can rewrite it in exponential form here, and so we can rewrite that as 2 to the x power equals 8. Okay, these are equivalent forms here. This logarithm is saying the same thing as this exponential here. Okay? And so then, now that we have this equation, what can we say the answer is? X is what? 3. It's got to be 3, right? And if you can't see that still, remember that 8 can be rewritten as a power of 2. 8 is 2 to the third. And so then, since 2 to the x is equal to 2 to the third, that means x has to be 3 here, right? We can have the same base. So here we were able to get a common base, and we say, okay, well, x is 3. So that's an example of a logarithm that we can solve no problem. Okay? We can do other sorts of like logarithmic equations. For example, we could have something like this. We could do like log, I don't know, base 4 of x equals 3. Okay. We can also solve this too. Okay. And again, we would solve it using that equivalent logarithmic form. Okay. So Amanda, I know you haven't been here the past couple of days, but can you rewrite that for us? Like if you saw how we rewrote this, how this here, the base of logarithm was 2, it became the base of our exponent. The x became the power, and the 8 swapped over to the other side there. So can you rewrite this one? How would you rewrite that one? 4x. Okay, so it'd be 4 to the, not the x, 4 to the what power? It's the other number, the 3 there. Equals, and then the x goes over to this side. Okay, that's how we would rewrite that. And so I'll just show you. So again, the 2 becomes the base. The 8 you see switch to the other side, and the x switched to be the exponent there. So it'd be 4 to the third equals the x, just like that. Okay, it's a little bit funky, but that's just the way we define a logarithm to be. And so then to simplify this, we can say, oh, what is 4 to the third? Well, 4 times 4, 16, times another 4, 64. And so there's our answer, 64. Again, we solved that logarithmic equation. Okay. Another way that you can think about solving this logarithmic equation, besides rewriting it in its equivalent exponential form, so what we did here is we took the logarithmic form, rewrote it in the exponential form. Another way you can think about doing this, though, is if you take log base 4 of x equals 3. Okay? Remember that logs are inverses of exponents, of exponentials. So for example, if I want to cancel out log base 4, I will raise this left-hand side to the power of 4. Or sorry, 4 to the power of that left-hand side. So I'll put that left-hand side in an exponent with a base of 4. And I'll do the same thing to the right-hand side. I'll take that right-hand side, put it in an exponent that has a base of 4. 4 to the log base 4 of x, that cancels, and we're left with just the x. 4 to the third becomes 4 to the third, which is again that 64. So that's another way to think about how this is working. We still get the same answer. Okay? So, with that being said, let's take a look at something that we maybe haven't seen before. Okay, for example, log base 4 of 5x minus 1 equals 3. Okay. To cancel out our logarithm here, with base 4, so we will again put a 4 on the left-hand side, 4 to the power of the left-hand side. So the 4 becomes the base, and we'll just raise that 4 to the power of the entire left-hand side here. And we'll do the same thing to the right-hand side. We'll do 4 to the power of 3. So 4 to the left-hand side equals 4 to the right-hand side. And we do that because, again, the log and the 4 are going to cancel, and we're left with just 5x minus 1. And then 4 to the third we know is 64. Okay, so that's really it. There's like one little step there that we had to do. And now we've gotten rid of the logarithm, we can solve this. Add 1 to both sides, we get 5x equals 65. Divide both sides by 5, we get x is 13. Excuse me. One thing we do want to do here is check, because there are such things as extraneous solutions. So we do want to check by plugging this into our calculator to make sure that we do get 3. So I'm going to take 5 times 13, and I'll subtract 1, whoops, and I'll take log base 4 of the 64. So again, you can do that one of two ways. If I want to do log base 4 of the 64, I can do log of 64 divided by log of 4. I see that I get 3, which works. Also, since I have the nice calculator, I can do log base, and then do log base 4 of 64 like that, and see again, I get 3. So either way, I see that it is in fact 3, so that is the right solution there. Okay, let's try another one. Okay, so we've got log base 5 of 4x minus 7 equals log base 5 of x plus 5. Okay. So, what can we do here to cancel out our logarithms? Yep, 5. Since they're both base 5, we can raise 5 to the left-hand side, and that's equal to 5 to the right-hand side there. So again, these become exponents of 5 on the left and the right. The 5 and the log 5, and the 5 to the log 5 cancel, and we're left with 4x minus 7 equals x plus 5. And then we just have this simple equation to solve. I'll subtract the x over, we get 3x. I'll add the 7 over to the other side, we get 12, and so we get that x then is 4. But again, we really want to check here that this does in fact work out. So let me see if I can get this to all fit. I think I can. There we go. And so I'll use my nice log base that I have. So I'll check log base 5 of 4 times 4 minus 7. I get that decimal, and I'll check the other side here. Log base 5 of 4 plus 5, which is just 9, so I can put a 9 in there. And sure enough, we get the same exact decimal. Okay, so you see the left-hand side and the right-hand side are the same, so we get 4. Okay. Another way you can think about this one, since we have log base 5 of something equals log base 5 of something, since they're both got to be equal and they're both log base 5 of something, you can just set those two somethings equal. We don't have to worry about the log base 5. You can just kind of get rid of it. So that's another way to think about it too. But of course, canceling it out is not a bad way to think about it too. All right, let's try another one here. Try another one. Okay. All right. How about this? Yep, it's an x minus 5 inside the logarithm there. Yep. So log of 2x plus log of x minus 5 equals 2. So we have two logarithms, and they're adding together to equal 2. Okay? So when you have two logarithms on the same side like this, combine multiple logs into a single log. Again, I'm just abbreviating for logarithms, using your properties. So here Greg is an example of how we're gonna, why the condensing of these can be useful. We have two logarithms we can't really solve. We want to combine that together, right? So before we start trying to solve, we want to combine those multiple logarithms together. We have two of them. Okay? And this goes back to what AJ said earlier. We have a sum. When you have a sum between two logarithms, what does that become in a single logarithm? A sum becomes what? What can we change that sum or that addition to be? Multiplication. So it's log of 2x times the x minus 5 equals 2. So again, two logarithms being added, they're the same base, so they become a single logarithm, and it's a product of the two things. And so I'm going to go ahead then and distribute that 2x to the x and the 2x to the minus 5 as well. So we get 2x squared minus 10x equals 2, like that. So now we've got our single logarithm. And when we had a single logarithm before, like for example in this one, we had log base 4, we used 4. Here, when we had log base 5, we used 5. Here we have just log though. What should we use? 10, right. Remember, and again, for those of you guys who weren't here, when a logarithm does not have a base written, that assumes it's base 10, okay? Like it assumes it's base 10. So we'll raise each side to be exponents for the 10. So 10 to the left-hand side equals 10 to the right-hand side. So we get 100 over here equals 2x squared minus 10x. The 10 and the log cancel, and then there's that. Okay, great. How do we solve this equation? Subtract what? Oh, it's a quadratic. So we want to subtract the 100 over to make it equal to 0. Very good. Yep, those quadratics, folks, we need to make them equal to 0 so we can use that zero product property. Okay, and now we want to factor this. You could use the quadratic formula if you wanted to, but let's see if we can avoid that. All right. Before we try and factor this using a product and sum, I see a GCF we can take out of here. What's the GCF we can take out? A 2. So I'm going to factor 2 out first to make the numbers a little bit smaller and hopefully not so awful to work with. Okay. So now that I've taken that 2 out, we can just think about trying to factor. See, I've taken the 2 out. We can factor just that x squared minus 5x minus 50. So we need two numbers that multiply to make negative 50, but add to make negative 5. Yeah, x minus 10, x plus 5. And now since these three things multiply to make 0, we can set them equal to 0. 2 equals 0 never, so we can forget about that one. X minus 10 equals 0, and x plus 5 equals 0. So in other words, x is positive 10, x is negative 5. Okay. We get two solutions. We got to check both of them to see if they work. Okay, got to check both of them to see if they work. So I'm going to go back up to my original equation here. I'll check the 10 first. So I've got, luckily it's all logs. So I can just do log of 20 plus log of 10 minus 5, which is just 5. I could have just done that. And I get 2, which is exactly what I wanted. Oh, sorry, you can't see it. There it is. Okay, we get 2. Now let me try plugging in negative 5. So we'll do log of, let's see here, 2 times negative 5 will be negative 10 plus log of, let's see, negative 5 minus 5, so negative 10. Oh, negative 10. And we get error. It's non-real. So in other words, negative 5, we throw that solution out, and only 10 works. Okay. If you want to be able to see this without having to check your calculator, here's how you'll be able to know whether your answer is going to work or not. If you plug in one of your solutions, and you end up taking the log of a negative number, you know that answer is not going to work. You cannot take the log of a negative number. Okay, it's not possible. There's no such value exists. All right, and I'll try and explain that here in real quick on the board. Let's imagine we're trying to take the log of like -2, which is really log base 10 of -2. Okay, imagine trying to evaluate that. Maybe that's hard because it's in terms of logarithms. So let's rewrite it in the exponential form. Let's say this does equal some value, and we'll just say it's some value x. We don't know what it is, so we'll just say it's x. Let's rewrite this. In exponential form, that means 10 to the x would equal -2. Do you see the problem with trying to come up with an x value here, that when you take 10 to that x value, you're going to get a -2? Okay. When you have an exponent, that means you're repeatedly multiplying. Can you repeatedly multiply a positive number to get a negative answer? No, it's impossible. And since this is impossible, then this logarithm, log base 10 of -2, is not possible. And it's true in general. Any negative number, you won't be able to do. Okay? So if you ever end up taking the logarithm of a negative number, you know that answer is not going to work. You throw it out. Okay? Let's try another one here. Oh, question, Greg.
Can you have a log base of a negative number?
Good question. So let's change it up here a little bit then. So we'll leave that now a +2, and let's make this now a -10. Oops. Use the same color here just for consistency's sake. Okay, and so again, we'll say whatever this is, let's say it equals x. So now it changes. So now we're going to take a -10 to the x, and we want it to be a +2. Okay? And so then the problem with this kind of math, or the problem with trying to solve something like this, is you might be...
If it was an even number, I suppose.
Yeah. If it was an even number exponent, it would become +2. But then the problem is, -10 is not a nice power, like there's no nice power -10 to give you 2, so now you're talking about like fractions, which potentially involves like square roots and stuff like that. And so, long story short, the answer is no. You'll never have a negative base for a logarithm. It's got to be positive. Not even 0 would work as a base either, because log base 0, again, you're now talking 0 to a power equals a number which is, is going to be impossible. It's got to be a positive number. Okay? So, yeah. All right. What the heck is that? Anywho. All right, so let's try another one. Like I said, let's try another one. How about natural log of 5x plus the natural log of x minus 1 equals 2. Natural log of 5x plus the natural log of x minus 1 equals 2. Okay. All right, so let's call somebody here. Let's go to Connor. You got an idea for us here, Connor, about what to do? We have a sum between these two logarithms. So a sum for two logarithms can become what? What can we change addition to be? What operation can we change it to be? Do you remember? No. So we can change it to multiplication. So here we have natural log of 5x plus natural log of x minus 1. It can become a single natural log, and then we'll just rewrite it as 5x times the quantity x minus 1, like that. Okay? Now, Connor, what can I do with this 5x here to simplify inside the logarithm? What can we do here? Yeah, and so what is that going to end up being?
5x squared.
Mm-hmm.
Minus 5x.
Good. Okay, now a natural log, there's no base written here, but what is base of a natural log, Connor? Do you remember? What number is it? And this 10 was if you have just the word log. So when you have like log of something, that's log base 10. When you have natural log, it's another number. Okay, so we'll see. Anyone want to help us out here? What is it? E, the number E. I know it's like, yeah, the number E, right? But yes, it's E. So in other words, to cancel out the natural log, we'll do E to the left-hand side equals E to the right-hand side. So the E and the natural log cancel, and we're left with 5x squared minus 5x, and then E to the 2 is, well, it's going to be E squared.
Did you ever write out like E squared as in like numbers?
You can, I mean, so again, E has a value. I'll show you here real quick. If you go to your calculator, you can either do like E to the 1, that would give us the value of E. It's like, there it is. Goes on forever. Okay. You can also just use E, second division sign, that's also the E value too. So this is interesting. All right, so we can't factor this, right? There's no way we're going to factor this. And I'm not going to make you use the quadratic formula. So let's instead use our calculators here and graph this thing. So 5x squared minus 5x minus E squared. Yep, go ahead. And so our solutions are the zeros there, right? We're going to find the zeros. So second trace, 0, because we want to know when our equation here is equal to 0. So I'll go to the left of my 0, hit enter. I'll go to the right of my 0, hit enter, and go in towards it and guess. So it's about negative 8.814. And then the other x value is going to be approximately, let me do the other one here. We'll go to the left. This is what I get. I actually altered a problem that was in the book here, and now I realize that was a mistake, but that's okay. We can still figure it out. So 1.814. Okay. Now, one of these x values is not going to work. Can anyone figure out which one it's going to be just by looking at the x values? One of these x values will not work. Which one is it going to be? The negative 0.814. When you plug the negative number in here, you're going to have 5 times the negative number, which is negative 5. You take the natural log of negative 5, and no good. The 1.814, it's positive, so times 5 will still be positive. 1.814 minus 1, still positive. I'll show you here. Just real quick, I'll show you that it works. Natural log of 5 times 1.814 plus natural log of 1.814 minus 1. 1.999. That's pretty close to 2. Pretty close to 2 there, right? So you can see that it works. Okay? Questions on any of that? So again, if you already have a single logarithm, like so, or you have a logarithm on both sides, like so, go ahead and just raise it to the base. So 4 to the left, 4 to the right, or here it's base 5, so 5 to the left, 5 to the right. When you have more than one logarithm on the same side, combine them together using our rules, and then use the base of 10 in this case, 10 to the left-hand side, 10 to the right-hand side, and then simplify from there. Okay? That's the idea. So, let me give you guys your assignment. That's all I have to go over with you here today. So I'm going to have you guys then, we'll work on the assignment here. Okay. So, what I would like you to work on, oh, they don't give you one of those spots. Okay. Let's see here. So on page 520, again, let's see here, I'm going to pick some nice ones. I'm not going to give you a billion of these to do, but I do want you to have a good sample size here. How about we do like 25, 27, 33, 41. I'd like to try 57 as well. That's a word problem there, but if you have enough information there to figure out. Yes, you should be able to figure that out, I think. If not, I can help you too, of course. Again, it's in your green books.